Hydrocarbons are any molecules that are composed strictly of just carbon and hydrogen, hence hydrocarbon. Yes, organic chemists have senses of humor too. Here's an example of a hydrocarbon. Nothing but carbon and hydrogen. And you'll notice we've got lines representing single covalent bonds. Now these covalent bonds are nonpolar because there's no oxygen, no nitrogen. Okay, this is your basic organic molecule. In this case, it's forming a line or a chain. Now they can also flip around to form circles. Now in this case, you'll notice that I've left out the hydrogens. If I were to put all the hydrogens in there, it would get kind of messy. In fact, oftentimes organic chemists will abbreviate it still further and just draw the shape of the molecule. Here you're given to understand that at each point there's a carbon. Okay. Now the question arises, how do I know how many hydrogens? How do I know that there's carbons here? Okay. Well, if you'll notice carbon, remember that carbon needs 4 electrons to share. So it can form 4 bonds. So if I only show one bond, one bond here, one bond here, this carbon is shown with only 2 bonds. So we know that there's hydrogen sticking off here. And with the abbreviation where I'm showing you just a shape, the points are showing where the carbons are, and I'm going to actually draw out the parts that are actually of interest. Okay. Now back to organic molecules. Carbon is considered the foundation of life because it can form these 4 bonds. Because it can form 4 bonds, it can form any shape you like by hooking up with a variety of different molecules. Now hydrogen is important in organic chemistry, but it can only form 1 bond. So you'll notice with each of these hydrogens, there's only 1 line going from each H. 4 from carbon, 1 from hydrogen. Now oxygen can form 2 bonds. So you're going to see just 2 lines coming from oxygen. Nitrogen can form 3. Sulfur can form 2. Phosphorus can form 5. As you look at these various hydrocarbons, you'll notice that they are all hydrophobic. They can't dissolve in water because they don't have any oxygen, they don't have any nitrogen. All of the covalent bonds are nonpolar, and so there's no charge. Now from here we're going to be talking about some functional groups. These are groups of molecules that you can add to your basic hydrocarbon to change its nature. Most of them make that part of the molecule hydrophilic. Okay, so let's go and talk about the functional groups. Now the way that I remember things is by remembering what's different. Of the different functional groups, there's one that's hydrophobic, all the rest are hydrophilic. So all I have to remember is the one hydrophobic one. There's also 2 acidic functional groups, I'll have you watch for them, and 1 basic functional group. So let's look at the methyl group. It is a carbon attached to 3 hydrogens. When you draw it out, it looks like this. Now, over here would be the rest of the hydrocarbon. So if you had to make a guess, would you consider this one to be hydrophilic or hydrophobic? It's hydrophobic. There's no oxygen, no nitrogen. Now the next one is the hydroxyl or alcohol group. It's an oxygen bonded to a hydrogen. Now because this goes as a group, we generally leave out the covalent bond between the oxygen and the hydrogen. But it's a polar covalent bond. Remember, the oxygen is stealing the electrons partially from the hydrogen, so the electrons are going woo woo, oh over here once, woo woo woo, over here once, and so we get a little bit of a charge. Now with this, when you add this to a hydrocarbon, it makes that part of the hydrocarbon hydrophilic, and it makes it so it can hydrogen bond with water. The book talks about ethers. Those are a bond. It's not a functional group, but it's where you take 2 hydrocarbons and hook them together by means of an oxygen. Now the carbonyl group is a double bonded oxygen that you put on to a hydrocarbon. Now it doesn't have a hydrogen attached to it, so it can't really hydrogen bond but it does make the molecule more hydrophilic because of this double bond. The oxygen is stealing those electrons part of the time from the carbon. So you get just a little bit of a negative charge, enough that water will interact with it. Now, when this is in the middle of a molecule, we call it a ketone. If it's on the end, we call a molecule an aldehyde. Later on in Chapter 5, you're going to see lots of ketones and lots of aldehydes. Now, let's talk about the carboxyl group. We call it this because it's kind of a combination of carbonyl group, where you have a double bonded oxygen, and a hydroxyl group. Okay, so we call it our carboxyl. And this is what it looks like. This is how it's going to be abbreviated in your text, COOH. This is what it looks like when it's drawn out. Here you can see you've got your double bonded oxygen, you've got your hydroxyl group. Now, this oxygen doesn't have a real good hold on this hydrogen. So this hydrogen has a tendency to leave its electrons with the oxygen and take off into solution. So this is an acidic group. It loses that hydrogen. Okay, and it becomes, this part of the molecule develops a full negative charge because the oxygen has the electron. Okay, so it's an acid. Now, if you're looking at a molecule and you're looking to see if it's an acid, you look for that negative charge. This next one that the book mentions is an ester. Once again, it's not really a functional group. It's a bond, but this time you have two oxygens hooking together. Now let's talk about the amino group. Oh, excuse me. This is what the ester group looks like, where you have a carbon with a double bonded oxygen, and then you have another oxygen there. Now let's talk about the amino group. This is a nitrogen with two hydrogens. Remember, nitrogens can form 3 bonds. This is what it looks like when it's drawn out. Okay, now this nitrogen has a tendency to pick up hydrogen ions from solution. So it comes along, and so this nitrogen has one extra proton in association with it than it has electrons. So this gives it a positive charge. This also makes it our basic functional group. So if you're looking at a molecule and you're trying to decide whether it's an acid or a base, if you see a positive on it, then you know it's a base. Okay? And in biology, it's generally going to be the amino group. Now let's look at the phosphate group. Now remember, phosphates can form 5 bonds, so we can stick all sorts of stuff on a phosphate. This is how you're going to see it in your textbook when it's abbreviated. This is what it looks like when it's drawn out. Okay, so you've got the rest of your organic molecule here. You've got your phosphate with 4 oxygens, one of which is double bonded. Now it has a tendency to lose the hydrogens off of these oxygens. It's just like the carboxyl group or the other acid group. And those hydrogens leave their electrons with the oxygens and head off into the solution, usually looking for an amino group. Okay, so this is our other acidic functional group. And our last one is the sulfhydryl. This is a sulfur attached to a hydrogen. Now this becomes important when we talk about proteins, because if you get 2 sulfhydryl groups together, they're going to lose their hydrogens and they're going to form a bond between it, and that has a tendency to stabilize proteins. So those are all of our functional groups.